Hello everybody, today I have another physics video. We're gonna go into kind of the introduction of period, frequency, all about circular motion. And we're gonna do so by examining the Europa Sentinel, which is a satellite that is going to travel to Europa, one of Jupiter's icy moons, and do some reconnaissance. As always, thanks to Krish Kotak for creating these problem sets that we get to work through. So the first problem that we're going to go through, also up here you can pause and examine this if you really want to read through the context of this problem. But for this first part, we're going to use the Pathfinder 1, which is a replica of the Sentinel. And it's going to kind of give us some information about how the Sentinel is going to act. So important things, we have the probe is attached to a 1.25 meter long arm, spun in a horizontal circle in a vacuum chamber to simulate the forces it will experience in deep space. It requires the probe to complete 10 full revolutions in 45 seconds with a mass 5 kilograms. First question is, what is the period of the probe's motion? The equation for period is time, so how long it takes, divided by number of revolutions, which we'll just call R. So in our case, this is going to be 45 seconds divided by 10 revolutions, which equals 4.5. And then this is seconds per revolution. In other words, it's going to take 4.5 seconds to complete one revolution. And that is the period. What is the frequency of the probe's motion? Frequency is given by 1 over the period. So 1 over period we'll call big T. This is 1 over 4.5. And this equals 0.222, and the unit for this is 1 over seconds, or hertz. For tangential speed, given the period, the equation is 2 pi times the radius over the period. So in our case, this is 2 pi, the radius is 1.25 meters, and a period is 4.5 seconds. Plug that into the calculator, we get 1.745 meters per second. That is the tangential speed. The magnitude of the centripetal acceleration is defined as the tangential speed, so Vt, divided by the radius, r. So this is equal to 1.745 divided by radius, which is 1.25. Apologies, I had the wrong equation written down for centripetal acceleration. It is actually velocity squared over radius, which a quick unit analysis can prove this. Velocity is meters per second, so velocity squared over radius would be meters squared per second squared over radius in meters. One of the meters cancels and leaves us with meters per second squared, which is the units of acceleration. But if you plug this into the calculator, you get that the centripetal acceleration is equal to 2.436 meters per second squared. Finally, say this is AC, it wants the tension in the arm holding the probe. We know that tension is a force, so tension is equal to the mass times the acceleration. And it's the only force in the horizontal direction. There's a force of gravity on it, but it would be counteracted by the normal force. So tension is mass times acceleration. The mass is 5 kilograms. The acceleration is 2.436 meters per second squared. If you plug them both into the calculator, you get that the tension is 12.18 newtons. So for this next problem, we have that the Europa Sentinel, so the satellite, has successfully deployed and it is beginning the approach to Europa. There's some information here about Europa and the problems we're going to answer down here. One important thing here is to assume that the Europa Sentinel is in a very low altitude orbit. So the radius from the center of Europa is approximately equal to Europa's radius. And the first question asks us to draw a free body diagram of the satellite, clearly labeling all forces. So down here we can draw Europa first. And we can say that here is the Europa satellite. And then there's a force of gravity pulling it to Europa. And then as the satellite continues around Europa, like so, it's the path of it, that gravitational force is going to continue to point inwards. So we know that gravitational force is a centripetal force, and that's important. And that gravitational force is the only thing acting on the Europa satellite there. So the next question asks us to write the algebraic expression for the gravitational force between Europa and the satellite. So gravitation, or the force of gravity, is given by the gravitational constant g times the mass of the first object, so we'll say mass of Europa, times the mass of the second object, so mass of the satellite, divided by the radius squared. And then that radius is going to be this distance here from the center of Europa. So, using this assumption here that they're approximately equal, we know that this radius is actually the radius of Europa. For the next question, question 3, we want to derive an algebraic expression for the orbital velocity of the satellite in given terms. The given terms are just g, the mass of Europa, and the radius of Europa. So we don't have the mass of the satellite. What we do know is that this is a centripetal force. So if we write centripetal acceleration, we know that it is tangential velocity, which is what we're looking for, divided by radius. And then this, so mass times centripetal acceleration, is the force of the centripetal force, which we can say is equal to the gravitational force, since it's the only force acting on the object and it's acting centripetally. So we can say that g times the mass of Europa times the mass of the satellite divided by r e squared, so the radius of Europa squared, is equal to, now this term is the mass of the orbiting object, so it is the mass of the satellite. Mass of the satellite times velocity squared divided by, this would be the radius of Europa, again using that approximation. So we can already cancel some things out. We can cancel the mass of the satellite, and we can cancel one of the radiuses just by multiplying them together. And we're left with, and then of course we can take the square root of both sides to get rid of this, because we're looking for just the velocity. So tangential velocity is then equal to the square root of g times the mass of Europa divided by the radius of Europa. And then the final question wants you to calculate the numerical value of this orbital velocity. So if you plug in our ME, RE, and gravitational constant g, you get that this is roughly equal to 1433 meters per second. For this next question, we want to raise the Sentinel to a higher, more stable orbit at an altitude of 300 kilometers above Europa's surface. So the first question is, what is the new orbital radius? This is pretty simple. Our previous orbital radius was 1560 kilometers. So we have that the new radius is equal to 1560, so that's the old radius, plus 300 kilometers. This is equal to 1860 kilometers, or 1,860,000 meters. The new orbital velocity, using this equation here, though in this case the radius of Europa is going to be our new radius, we get that v new is equal to the square root of g times the mass of Europa divided by r new. And if you plug this into the calculator, you get 1312 meters per second. And if you're following along, you can come up here and pause to see the mass of Europa here and the gravitational constant here, which you would plug in as is, since they're in terms of kilograms and Newton meters and kilograms. So you don't need to do any unit conversions there. The final question asks us to calculate the time for the satellite to complete one full orbit, aka its orbital period, in hours. Earlier, we used the equation that velocity is equal to 2 pi times the radius divided by the period. So we can rearrange this equation to solve for the period instead, by multiplying by period on both sides and then dividing by velocity. We get that the period is equal to 2 pi times the new radius divided by the new velocity. If you plug in our new velocity here and our new radius here, you get that the period, or the time that it takes to complete one full orbit, is 8,907.7 seconds. But since it's asking for it in hours, we divide this by how many hours are in a second, which is 3,600. So we multiply it by 1 hour divided by 3,600 seconds, and we get that the period, t, is equal to about 2.47 hours. For this last problem, we have that there's an astronaut on board the Sentinel craft as it orbits around Europa, as it approaches Europa, actually. I'll let you read through this paragraph to get the exact context, so pause and do so. But the key information is that the astronaut has a mass of 75 kilograms and that the spacecraft accelerates at 2.5 meters per second squared away from Europa's center. First question is to draw a free body diagram for the astronaut during this maneuver. So we'll say that this is our astronaut. Label him A. There is still a force of gravity from Europa acting on the astronaut. And then since he's on a scale, there is a normal force pressing against him. And then one key thing to realize, which I'm going to draw in red, this isn't really part of the free body diagram, but it may help you realize what's happening or visualize it, is that there is an acceleration in this direction, so away from the center of Europa, at 2.5 meters per second squared. So in my case, Europa is somewhere down there. That's the surface of it. So we can say that the net force, so this is solving question 2 now. So what is the astronaut's apparent weight? The net force is equal to the normal force from pressing on the scale minus the force of gravity. And we can't just say that they're equal to each other, because if they are, then the net force is 0. And we know that the net force is not 0 because it is accelerating away from Europa's center. So to solve the problem, we can instead set it equal to the mass of the astronaut times the acceleration. The astronaut is in the spacecraft, so he is going to be accelerating at the same rate as the spacecraft. So we know that this A is equal to our 2.5 meters per second squared, whereas this M is equal to our 75 kilograms, so the mass of the astronaut. But let's solve symbolically first. We know the force of gravity, which is we calculated it earlier, the force that Europa exerts on the astronaut. We don't know N, and that's what we're going to solve for. So rearranging, we have that N is equal to mass times acceleration minus the force of gravity. So in this case, N equals mass times acceleration. Sorry, this is plus force of gravity. I forgot I moved it to the other side. So N is mass times acceleration plus G, and then this is gravitational force on the astronaut. So this is going to be the mass of Europa, that's our first object, times the mass of the astronaut, which we're just going to call M. Divided by the radius of Europa squared. We'll say that in this case, since it's approaching Europa, we'll say that it's right up by the surface. So the radius is roughly equal to the radius of Europa again. So now this, we just plug in our known values. So we get that N is equal to the mass of the astronaut, which is 75, times the acceleration, which is 2.5, plus G times the mass of Europa times 75 divided by the radius of Europa squared. For a refresher, those values we were using earlier are right up here, if you'd like to plug them into your calculator yourself. I plugged them into my calculator though, and we get that this is equal to 286 newtons. This is equal to the normal force, and that is the apparent weight during this brief acceleration. This is the exact same method you would use for an elevator problem. Somebody's accelerating upward in an elevator, or downward in an elevator, and so you can determine the apparent weight using this same method. Though in this case, the force of gravity obviously would not be this, it would be mass times 9.8 meters per second squared. But that is the end of this video. If you have any questions or comments, please leave them down below. And as always, good luck with all of your tests and exams, and I hope that this helped you out.